When you look up at the night sky, you are seeing history. Every pinprick of light is a memory, a messenger that left its home millions or even billions of years ago, to find your eyes tonight. Between those distant suns stretches a silence so vast that numbers lose their meaning. And yet hidden within that silence is motion, the slow breathing of the universe itself. For most of human history, we believed space was empty, cold and perfectly still, a stage on which planets and stars performed their celestial dance. But in the early years of the 20th century, a young patent clerk named Albert Einstein dared to imagine something different. He wondered, what if space and time were not separate things but part of a single living fabric? What if that fabric could bend and stretch, twist and ripple, shaping everything that exists? This idea became one of the greatest revolutions in human thought, the theory of general relativity. It told us that space and time are dynamic, that gravity is not an invisible pull, but the gentle curvature of the cosmic fabric itself. In this vision, matter tells space how to curve, and curved space tells matter how to move. To picture it, imagine a vast ocean without surface or edge. Drop a stone into that ocean, and ripples spread outward, distorting everything around them. Now imagine that ocean exists not in water, but in the geometry of reality. Every star, every planet, every atom distorts the fabric of space-time like that stone. And those distortions guide the paths of everything else. Einstein's insight began as a whisper in his mind, a quiet question about how light and time might behave for someone falling freely through space. He imagined an elevator in free fall. Inside it, a person and everything around them would float weightless. In that instant, gravity seems to vanish. From this simple thought, Einstein glimpsed a deeper truth. Locally, free fall and weightlessness are the same thing. This was the seed of a principle that would reshape physics, the equivalence of gravity and acceleration. From this seed, an entire universe blossomed. Einstein realized that if gravity and acceleration were equivalent, then the effects of gravity on light and time could be predicted by geometry itself. A beam of light passing near a massive star should bend, not because the light is pulled, but because space-time itself is curved. Time near a massive object should slow down, not because clocks malfunction, but because the flow of time depends on where you are in this curved landscape. To most people of his time, these were wild, almost mystical ideas. Space and time had always been seen as fixed, eternal, absolute. But Einstein's vision was dynamic, a cosmic fabric that responded to energy and matter, flexing under their weight, vibrating with their motion. It was as if the universe itself were alive. For years, Einstein worked alone, guided only by his intuition and the pure logic of mathematics. He sought equations that could express this intimate relationship between geometry and gravity. Late in 1915, after a decade of struggle, he found them. They were simple in appearance but profound in meaning. The curvature of space-time equals the energy and momentum of matter and radiation. These equations became the foundation of general relativity. When Einstein presented his new theory, it seemed almost too beautiful to be true. And like all bold ideas, it demanded proof. The first came in 1919, when astronomers observed a solar eclipse. As the moon blocked the sun, stars near its edge appeared slightly displaced. Their light bent as it passed through the curved space around the sun. The amount of bending matched Einstein's prediction exactly. Overnight, he became a global symbol of genius, but fame was never his goal. Einstein's real reward was understanding, the deep, quiet joy of seeing how everything fits together. He had built a bridge between the mathematics of geometry and the physical world, revealing that gravity is the shape of space-time itself. General relativity was not just a new theory of gravity, it was a new language for describing reality. It told us that space can expand, time can slow, and the universe can evolve. It predicted phenomena that seemed almost impossible: black holes, gravitational waves, the expansion of the cosmos. It even hinted that the universe might have had a beginning. For centuries, we had imagined the cosmos as infinite and eternal. But Einstein's equations suggested that space could stretch or contract, like the surface of a balloon being blown up or deflated. A few years later, astronomer Edwin Hubble looked through his telescope and saw galaxies rushing away from us in every direction. The farther they were, the faster they moved. The universe was expanding. Suddenly, Einstein's abstract mathematics described something breathtakingly real. If the universe is expanding today, it must have been smaller yesterday, smaller still the day before, until long ago, everything was compressed into an unimaginably dense, hot state, the origin we now call the Big Bang. General relativity had opened the door to modern cosmology. As the universe expanded, it cooled, allowing matter to form from pure energy. In time, gravity gathered that matter into stars, galaxies, and eventually into planets like our own. The same equations that describe the bending of starlight could also describe the birth of galaxies and the flow of cosmic time. Yet Einstein himself was uneasy with the idea of an expanding universe. He had imagined a cosmos that was static and eternal. To make his equations fit that belief, he introduced something new, a cosmological constant, a kind of anti-gravity that balanced the attraction of matter and held the universe still. But when Hubble's discovery proved the expansion was real, Einstein abandoned the constant, calling it his greatest blunder. Ironically, decades later, scientists would bring it back to explain another mystery: the accelerating expansion of the universe, driven by what we now call dark energy. Through the lens of general relativity, we began to see that the universe is not a fixed stage, but a story unfolding through time. Galaxies drift apart like embers carried by a cosmic wind. Space itself stretches, and with it, the rhythm of time changes. Somewhere in this vast expansion, stars die, collapsing under their own gravity to form black holes, regions where curvature becomes so extreme that even light cannot escape. A black hole is the most dramatic expression of general relativity. Imagine a star many times heavier than the Sun. When it exhausts its fuel, its outer layers explode in a supernova, but its core collapses inward. Gravity crushes it smaller and smaller, until all its mass is concentrated in a single point, a singularity where the known laws of physics cease to apply. Around it forms an invisible boundary called the event horizon. Anything crossing this horizon is lost to the outside universe, trapped by the curved geometry of space-time itself. At first, Einstein doubted that such objects could exist. They seemed too extreme mathematical curiosities, rather than real things. But in time, evidence mounted. Astronomers observed stars orbiting invisible companions, moving at tremendous speeds as if drawn by unseen masses. Later, telescopes detected the faint X-ray glow of matter spiraling into these dark hearts. And in 2019, humanity saw the first actual image of a black hole's shadow, a glowing ring of light surrounding the darkness at its center. It was Einstein's theory painted across the sky. Yet the story of general relativity does not end with black holes. The same equations also predicted something subtler: waves in the fabric of space-time itself. Just as a stone dropped into a pond sends ripples across the water, massive objects in motion send ripples through the geometry of the universe. These are gravitational waves. They carry energy, stretching and squeezing space as they pass. For a century they remained theoretical, too faint to detect. Then in 2015, the LIGO Observatory caught their faint whisper, a signal lasting less than a second, the aftershock of two black holes colliding more than 1 billion light-years away. It was a moment that confirmed Einstein's dream and opened a new window on the cosmos. Gravitational waves let us hear the universe for the first time. They tell stories that light cannot, of invisible mergers, of neutron stars and black holes locked in cosmic dances, of events too dark to shine but too powerful to ignore. With each new detection, we add a note to the symphony of space-time. Even today, general relativity continues to shape how we understand everything from the motion of planets to the birth of galaxies. The GPS signals that guide your phone must account for relativistic time dilation. Without Einstein's equations, your map would drift kilometers off course every day. When we study the early universe, simulate the collision of black holes, or trace the bending of light around distant galaxies, we are using the geometry he revealed. But the theory also points to its own limits. At the heart of every black hole, and at the beginning of the Big Bang, the equations break down. They predict infinities, places where curvature becomes infinite and time loses meaning. To truly understand these regions, we will need a new theory, one that unites Einstein's curved space-time with the strange quantum world of atoms and particles. For now, though, General Relativity remains one of humanity's greatest achievements, a work of art written in the language of mathematics, yet alive with poetry. It tells us that space can bend, time can stretch, and the cosmos itself is a restless, evolving being. When Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible, he was expressing this wonder, that our small minds,